Good afternoon, everyone. I'm Konstantino Listovski. I work at CEA, and today I'm presenting Pierre Letournel's PhD's research work. So Pierre is currently rushing and trying to wrap up his manuscript, and I will be presenting his results. I'm co-supervising with Marc Bocquet at CEREA, mostly for the data assimilation part. So the idea of using microbaromes to investigate atmospheric states is not new, and I will briefly come back on this, as well as on our objectives. So I will explain how we process our observations, simulate our observable, and trying to compare both to come up with some diagnostics on the actual performance of the atmospheric states as they are modeled. And then we'll go one step further and try to explain to see how we can assimilate microbaromes and try to update the atmospheric states through data assimilation. So you may have heard already of the voice of the sea, which something was described by a Soviet scientist, Shuleikin, who understood that some waves were emitted by the sea surface. And they understood that some sonic waves were coming out of the sea. And so in 1939, Benioff and Gutenberg coined that term microbaromes by analogy with the macroseisms. And it was in the 70s that Don and Rin had a series of papers explaining how microbaromes could be used to investigate the atmosphere. And in their studies was a lot about the thermosphere, or at least the lowest layers of the thermosphere. And since then, there has been, it's non-exhaustive, but there has been many studies trying to use microbaromes to say something about the atmosphere. And for instance, Metz and Evers imaged the life cycle of a sudden stratospheric warming using microbaromes observations. Patrick Hooper and colleagues used microbaromes to validate some bias that were first determined by comparing LiDAR measurements to the atmospheric models. And Vorobeva et al. In two different papers at North-SAR use microbaromes to try to investigate the state of the polar vortex. And then I want to come back on this notion. When I say polar vortex, I mean the polar vortex in the stratosphere, which drives the acoustic waveguide at mid and high latitudes for infrasound. And I wanted also to remind that, so microbaromes, which is the oceanic ambient noise, coherent noise, so it's a global source, but with hotspots in terms of amplitudes, but there are also dominant frequencies that will depend on the size of the basin, of the oceanic basin, or the sea which is emitting those microbaromes. So the larger the basin, the longer the fetch, and so the lower the dominant frequency. So why do we do this? So numerical weather prediction models that are obtained by national data centers, from weather centers, or by the IDC are biased in the middle atmosphere. And one of the reasons is that because there is a lack of data above 30 kilometers, mostly, especially in terms of winds. And so microbaromes could serve as a source, because they depend on winds above 30 kilometers, could serve as a source to probe the atmosphere and bring some additional data and constraints for modeling. And so for infrasound source localization characterization, well, you know that we need to have reliable models. And so why not trying to improve the models by using the microbaromes? And so there are two objectives here. First, trying to develop a tool to diagnose the relative performances of atmospheric models in the middle atmosphere, but also to go one step further and try to use microbaromes in a data assimilation framework to update the modeling. So here, let's use the IS-37, very good station in Norway. And here, this is a polar histogram view, yearly, 2021, showing that mainly there are 3 hotspots of microbaromes, like the Atlantic Ocean, the Greenland Sea, and the Barents Sea. The color codes for the frequency, and you see already what I said before about the dominant frequency being different depending on what source of microbaromes you're looking at. But Pierre didn't use PMCC, which was used for this polar histogram, but used MCML, so the multi-channel maximum likelihood estimator, which is a likelihood which relies on the maximization of a likelihood estimator with a grid search approach, azimuth versus wind speed. You see the grid here. And so what Pierre does is keeping the information along the azimuth, averaging everything within a range of relevant trace velocity to end up with a microbarometer azimuthal distribution at the station, the smooth distribution you see on the right side. So this is for the observations. On the modeling side, we've been using, Pierre has been using the source model product Arrow, which has been developed during Marine de Carlo's PhD thesis between CEA and Ifremer. So it's a product providing acoustic intensity in grid cells. And there is an operational product that is documented in this reference. All the references are at the end of the presentation. You can show it on with the app by downloading the presentation. So it's an available product. And on the propagation side, what we do is that every source element propagates to the station, and then all the acoustic powers of all the source elements are summed up for each direction. And then we end up with an azimuthal distribution, which is modeled. And so for the propagation, we've been using parabolic equations with the NCPA probe software. And I will explain why we also moved to a surrogate approach, a neural network approach for the data assimilation part, and I will explain that. So now, can we use this distribution to compare to the observation? Well, as such, the answer is no, because we need to account for the antenna response and also for the response of the processing algorithm itself. And so the way Pierre does it is that, he starts with a model distribution at the top. Then he generates some synthetic signals for every direction that he will sum up to come up with a signal. He will delay the signal according to the sensor positions and reprocess that through the MCML to account for both at the same time the array response and the algorithm the array processing algorithm response itself. And so we end up with a smoother distribution at the bottom here of the slide, which is more resembling the one I was showing when I explained the observation part. And so then you have distributions. You can put side by side all the distribution through time. So the y-axis each time is the azimuth for cardinal points, and time on the x-axis. The top plot is a simulated soundscape of microbaromes using the WACAM model, so the whole atmosphere community climate model, which is a high-top model. In the middle are the observations, and at the bottom is an implemented metric, a distance, which allows to systematically quantify the difference between the observation and the modeling. And so a general comment is that the x-axis starts in January 2021. So during the winter, when the polar vortex is firmly set, model observations agree the most. And during the transitions, the equinoxes or the summer, where the guiding is looser, is more loose, it's more difficult for the model to always agree. And so the metric, the distances are larger. But you see here that during the January months, you have some spikes in the distance. Those are not artifacts. Those are due to a sudden stratospheric warming occurring and completely reversing the guiding, leading to summer-like conditions. And so focusing on the January part, you see two simulations. A top plot, one with a hybrid approach using ECMWF atmospheric products reanalysis that are augmented by a climatology on top of it, because ERA 5 stops at 80 kilometers. So IWM and MCIS are used on top of ERA 5. This is why I call it the hybrid approach. And you have again, WACAM model used in the middle, the observation below, and at the very bottom part of the slide, there is again the distance, the metric which is used for both, for comparing both the hybrid approach in blue with the observations and the WACAM modeling with the observations. And you see that at two instances, when there is those jumps in the westerly detections of microbaromes due to the sudden stratospheric warmings, the WACAM model is performing better, and this is proven by the distance which is lower. So a quick explanation for that is that the WACAM being a high-top model, it represents better the vertical coupling occurring during the southern stratospheric warmings, which reverses the guiding. And there are impacts to be accounted for in the mesosphere as well. For instance, the reason for why WACAM is better representing the observation in the first, between like the 1st and the 7th of January is because the mesosphere is better represented within the WACAM model, because the southern stratospheric warmings also impacts what's happening in the mesosphere and the lower thermosphere as well. And now, so we have this top view of the top plot with the WACAM model, and we introduced a neural network for that. And this is a comparison between both, and I will not go into the details of that. Alice Camejo has at CEA developed this neural network based on parabolic equation outputs. And so what is interesting with the neural network when we use Python and TensorFlow is that you can automatically differentiate the propagation model. And to us, it was less straightforward to see how to do that with the software and the code from NCPR Pro itself. So we use the CRNN for that, the convolutive recurrent neural network. And so we have the ability to derive gradients because it's differentiable. So using the gradients, we can see how the whole chain is sensitive to the atmosphere and also to the source. Because if you claim that you can say something about the atmosphere, you want to be sure that you are more sensitive to the atmosphere than you would be to any change in the source model. And this is what we do here with the red curves referring to the atmosphere, to the sensitivity of the processing chain to the atmosphere versus to the source. But now let's jump into the data assimilation world. This is the last slide. And so the 3D VAR approach consists essentially in minimizing a cost function which accounts from what we know from the observations, what we know from the modeling, and the solution of this problem is what we call the analysis, the update of the atmospheric model. And so here the distributions, this is synthetic observations because it's easier to start with this. And so we see the background, the prior is the blue distribution, the observation, the synthetic one is the red curve, and the green curve is the analysis, and it goes closer to our observation. Here we'll be using an idealized case because we've been describing the atmosphere with empirical ectogonal functions. Like here, only 4 EOFs are used, but it was to test the chain and to see how it would respond. And on the right side, the analysis below are the waveguides because it's multidirectional. This is the big advantage with this global source. It's multidirectional, sorry. And so the background's at the top, then the observations in the middle, and you see that with the analysis, we get much closer to the observation, starting from the background. So now I will conclude here. So what we have is a proof of concept to bring diagnostics for atmospheric products in the middle atmosphere, but we manage, and Pierre managed actually, to have a differentiable processing chain, which is key and needed when you want to do data assimilation. And of course, there are a lot of improvements to be made, starting, for instance, with the way to deal with local minima, because we also, when we increase the number of EOFs and complexify the description of the medium, we ended up having also a local minima, which of course is a problem when you want to minimize the cost function I spoke about. And I think I'll stop here, and I'm happy to take any questions. Hey, thank you.
Thank you, Constantino. It's very nice work. Question, please. Yeah, please, and thank you.
Thank you. It's really nice work. So I guess my question will be about the differentiability of the source and the propagation part. So I saw that there's a lot of covariance. And so it's very important indeed to factor that out, the source term versus the propagation part. So can you go maybe back there and tell me a little bit more about how this really works? It was a little fast for me.
Okay, you mean in terms of the...
Yeah, like where you see that the data provides information about the atmosphere versus variability of the source.
So okay, so the starting point perhaps to consider is like what are we comparing? We are comparing two distributions, azimuthal distributions, and so the observable is simulated through the observation operator, which starts with the source model and then propagate the source elements to the station. And so there are errors that are attached to the source model, that are attached to the surrogate, the neural network, and are propagated within the error covariance matrices that are used within the framework of data assimilation. So everything propagates to the very end of your chain. And so on the distribution I showed, there are also errors that are included.
But could you pull up that slide that shows the time series? Yeah, that one.
Okay.
So there's...
Here is the sensitivity, which is defined with the gradient of the operator times the error we inferred for the source model and for the atmosphere for this plot. But then the error induced by the neural network is also included within the whole cost function, which is minimized through the matrices that are used within the minimization of J, of the cost function. So all the errors are included within the process.
I think I have to read the paper and come back to you with more questions.
So the paper is more about the diagnostic tool.
Yeah.
Everything which is about data assimilation is really like happening more or less now. So there is no paper to it. But the PhD manuscript will be written in English. So it will be easier, I guess, to communicate around it. Yeah.
Okay. And thanks for the work again. Yeah.
Thank you.
I think so. Yeah, thank you. Moving to the next presentation, which will be online.